Welcome everyone to part one of our code along, where we're going to create a generative adversarial network to generate MNIST data digits. Let's go ahead and open up a notebook and get started. All right, let's start with our imports. We'll do TensorFlow, of course, as TF, and then we're also going to be using NumPy, and we'll be plotting out just a little bit just to see what the numbers look like. So let's go ahead and import pyplot, and we'll say matplotlib inline. Okay, so let's go ahead and grab our data. Remember, TensorFlow has a really nice function that allows you to quickly grab the data. So you need to say from examples, tutorials, MNIST, import input data. And then we're going to say MNIST is equal to input underscore data. And we're going to say read data sets. And I'm going to pass in the exact file path from the notebook. That way I don't accidentally re-download all the data. So I'm just going to copy and paste this to make sure I don't mess it up here. There we go. So I'm going to grab it again from the convolutional neural networks MNIST dataset. So when you run this, you should only see extracting if you're running this in the same folder as the notebook expects. So keep that in mind, that way you don't need to download everything again. So as a quick review, remember, if we want to show the data, you can say MNIST training set, and then there's images here, and you can grab just some random image in here, so whatever is the 12th indexed image. And then you need to reshape it to a 28 by 28 pixel. Run that, and that should show you whatever image it is. In this case, it's a 1. So if we check out another image, then this one looks like a 2 or a 9. This one's a 7, clearly. Okay, and then remember that we can also say CMAP, so we can say grays here, just to see the actual white background. All right, now it's time to actually build out the networks. The first network we're going to start with is the generator network, and then we're going to create the discriminator network. And for both these networks, we're going to create what's called a variable scope. So let's first start with some functions. So we're going to create a generator function, that way we can easily call it. It takes in z as an input. Z is going to be that random noise that we start the generator with. And then it's going to have this reuse variable that we'll explain later on when we talk about the variable scope. So we'll say with tf variable underscore scope. We're going to pass in a string code here. So if you do shift tab, you can see that there's a name or scope here. So you can pass in a string code. We'll say GEN for generator. And then we're going to say reuse is equal to reuse. So you can either set this reuse as none, or later on what you're going to see is we'll set it as true. So you might be wondering, well, what is this variable scope for? Well, the goal of variable scopes in general is to allow you to basically have modular sections or subsets of parameters. So those belonging to certain layers, that way when an architecture of a layer is repeated, so when you call this generator function again, the same names of those variables can be used within each layer scope. That's going to make a little more sense when we actually see how we use this function, because we're going to be using it over and over again. So keep that in mind, that we're going to be using this variable scope, and this reuse we're going to pass in later to be true. So we'll kind of touch on that later on. But for right now, we'll set the hidden layer first. So say tf layers, and it's going to be a dense layer, so densely connected. The inputs here is just going to be that random noise z that we'll create later on. And then the number of units, we'll just say 128, as we did before when dealing with the MNIST digits dataset. And then what we're going to do here is, for our hidden layer, the activation function we're going to be using is a leaky rectified linear unit. So remember, we talked about leaky rectified linear units when we were talking about various activation functions. Unfortunately, TensorFlow in 1.3 still doesn't actually have a leaky rectified linear unit. And if you look this up on Stack Overflow, let me bring in the link real quick, you'll get something like this where someone's asking, well, how can I use a leaky rectified linear unit? And there's a couple of good answers here. Let me zoom in so you can see this. If you take a look, one of them actually just defines the full function here, and then another person has a really clever solution where you just use tf.maximum x or versus alpha times x, where you choose that alpha, basically essentially the leak rate of that leaky rectified linear unit, and this is a lot more efficient to use, so we're going to be using that. And you'll notice that the very last post, answered pretty recently, is that there's going to be a leaky rectified linear unit upon the release of 1.4, which at the time of this filming isn't out yet, and the environment file we provide is not using 1.4. So eventually in the future, you'll just be able to pass in tf.nn.leaky rectified linear unit as the activation function here. Because remember, for these layers, if you do Shift Tab here, there's going to be an activation option. Okay, so let's go ahead and do the maximum method. So if we come back here, we're going to be using this maximum method to simulate the activation function. So let's come over here and start typing that out. So we're going to choose an alpha of 0.01 for our leaky rectified linear unit, and then we're going to do that kind of maximum logic here. So we'll say TF maximum, and we're going to say alpha times hidden 1 or hidden 1. So it's basically just going to choose the maximum out of that. And then we're going to do another hidden layer. We'll say hidden layer 2. Again, that's going to be TF layers densely connected. The inputs for this one is going to be the out or hidden 1, and we'll have this be 128 units again. And that's, again, something you can play around with how many units you want. If you wanted to, you could have a really, really large network if you wanted very good generation results, but 128 should be more than fine. In fact, you can kind of play around with if you only want one hidden layer. But let's say hidden 2 now is going to be the same thing, TF maximum, and it will be alpha times hidden 2 or hidden 2, whichever one's maximum there. Okay, finally we're going to have our output, and that's going to be TF layers densely connected. We'll take in hidden layer 2, and then the units here, because this is the output and we're actually generating a new picture, we're going to have the full 28 by 28. So we expect 784 to be our output here, because we're actually trying to generate that vector image. And then the activation function, when kind of playing around with this, I noticed that the hyperbolic tangent tended to work better than a sigmoid, so we'll go ahead and set up our network to use that. So we'll say tan H there. And later on you'll see that when we're passing in random noise, instead of going from 0 to 1, we're going to go from -1 to 1, just like the hyperbolic tangent does. And then finally we're going to return the output. Okay, so that is our generator function. We're going to do something really similar for our discriminator. Remember, the discriminator is going to try to tell whether something is real or fake from the generator. So let's go ahead and make this a discriminator. And this is not going to take in Z, instead it's going to take in data, X, but it will have this reuse, and instead of gen here, we'll go ahead and say DIS for the discriminator. Hidden 1, that's going to be the same thing, except the inputs here is going to be X. We'll go ahead and do the leaky rectified linear unit using this method of alpha. So this is going to be the same. This is again going to be the same. We'll have 2 hidden layers here. And at the very end, instead of this activation function being a hyperbolic tangent, we just want to know true or false. Is it a real data point or not? So what we're going to do is separate this out into 2 steps. We'll say the logits themselves, TF layers, dense, pass in hidden 2, and say units is equal to just 1, because we basically want the probability of it being real or fake. And then we'll say the output is TF sigmoid of the logits. Okay, so that's our discriminator. So now we have these 2 functions that we're going to be able to quickly call upon when we want to build out our generators and discriminators. Okay, so in the very next lecture, what we're going to do is begin to actually use these functions along with some placeholders and then define a loss function as well as the optimizer. I'll see you at the next lecture.